After understanding Faraday's law of induction and understanding his experiment, let us see some examples. Example 6.1. Consider experiment 6.2. Experiment 6.2 was that where one big coil was there, another small coil was attached to a battery. But there was no key. What would you do to obtain a large deflection of galvanometer in this experiment? So there was no key and it was a coil. How would you demonstrate the presence of an induced current in the absence of galvanometer? So we have two situations. First, what will we do to get a large deflection? First thing. And suppose if we don't have a galvanometer, how can we say that there is a current? So let us solve this problem. To obtain a large deflection, one or more of the following steps can be taken. So we can do any of these. Use a rod made of soft iron inside the coil C2. Suppose we put this soft iron rod in this coil. So what will happen? This magnetic field will increase. Magnetic field will increase because of this soft iron core. Connect the coil to a powerful battery. Second thing is a powerful battery. Instead of this single battery, we have a multiple battery. So current will increase. Current increase will gives rise to magnetic field increase. So this will give more EMF. Third thing is the move the arrangement rapidly. Rapid movement towards the coil. So three things we have. We can put a soft iron core. We can attach a powerful battery. And third thing is we can move much more rapidly. Now second part. Suppose if we don't have a galvanometer, what would we do? Replace the galvanometer by a small bulb. So we put a small bulb here, the kind one finds in a small torch light. So if we put a small bulb that we find in a small torch light, that will also work as a galvanometer. The relative motion between two coils will cause the bulb to glow. So bulb will glow, but only problem with the bulb is that it will not tell us in which way current is going, and thus demonstrate the presence of an induced current. So this bulb will tell us that there is some kind of induced current. In the experimental physics, one must learn to innovate. That means find new ways. Michael Faraday, who is ranked as one of the best experimentalists ever, was legendary for his innovative skills. So we have to learn innovation. That means how to make situation according to ourselves. So what did we do to make situation as ourselves? If we don't have the galvanometer, we can use a small light bulb. Now example 6.2. A square loop of side 10 centimeter and resistance 0.5 ohm. So we have a square loop and side is 10 centimeter. Resistance of the loop is 0.5 ohm, is placed vertically in east-west plane. A uniform magnetic field of 0.10 Tesla is set up across the plane in northeast direction. So this is the direction of the magnetic field. The magnetic field is decreased to 0 in 0.70 second. So now they are reducing the magnetic field, and in 0.7 second it is decreased to 0 at a steady rate. So that means it is not immediately become 0, slowly it is going down. So previously it was 0.10 Tesla and now it is 0. So this is slowly going down, and what is sudden? So it is 0.10 suddenly goes down. So this is not sudden change, it is going down slowly this magnetic field is reduced. Determine the magnitude of induced EMF and current during this time interval. So we have to determine what is the induced EMF and what is the current in this time interval. So side of the loop is 10 centimeter, resistance is 0.5 ohm. This magnetic field initially was 0.10 Tesla, time is 0.70 second, and magnetic field, final magnetic field is 0. At the angle theta made by area vector of the coil with the magnetic field is 45 degree. But how do we get this angle of 45 degree? So let me make some diagram. So this is north, this is south, this is east and this is west. Now this loop is in vertical position in this east west direction or east west plane. Now what is the area of this? Area vector is in this direction, area vector is in this direction and magnetic field is in this direction, northeast direction. So this total angle from north to east is 90 degree and this is northeast. So this angle is 45 degree, half of this. Total angle between north and east is 90 degree, but since this magnetic field is in northeast direction, that means the angle is 45 degree with the normal to this loop. So we get this angle to be 45 degree. Now we know that this phi is equal to BA cos theta. What is the value of B? 0.1 Tesla. And what is the area? Now let us calculate the area. For a square, area is side square and side A is equal to 0.1 meter because A was given as 10 centimeter. 10 centimeter means 0.1 meter, that is 10 to the power minus 1 meter. So this B is 0.1, this area is equal to this A is equal to side was 10 centimeter, A square is 10 to the power minus 2 meter square, that is area, 10 to the power minus 2, and cos theta is cos 45, cos 45 is 1 by root 2, cos 45 is 1 by root 2. So what do we get? We get 10 to the power minus 3 upon under root 2 Weber. 10 to the power minus 3 minus 2 and minus 1, we get 10 to the power minus 3 upon root 2. So this is the magnetic flux. So this was initial flux. Final flux was 0 because magnetic field was reduced to 0. When this becomes 0, so we have no flux. When magnetic field is 0, there is no flux. This is the final flux. Initial, final. The flux, the change is flux is brought in about 0.70 second. So how much time is given? 0.7 second. So now we have to put these values. From equation 6.3, the magnitude of the induced EMF is given by, so what was the equation? E is equal to minus d phi b upon dt. So this was the equation, Faraday's law. So instead of this minus sign, let us take mod, that means value only. Let me remove this sign. So we have removed the sign. We don't know what is the direction, but we know what is the value. So epsilon is equal to delta phi upon delta t. So we have changed d with delta. What is difference between delta and d? When steps are so small that we cannot measure them, then we use d, that is differential form. When steps are measurable, because here we can measure 0.1 minus 0, delta t is 0.70 second. When we can measure them, then we use delta. When steps are so small, that means we have to use differential form, then we use d. So now let us put how much change has come in phi. So this is initial value, this is final value. Phi minus 0 and this is time difference is delta t in 0.70 second. So initial value was 10 to the power minus 3 upon root 2. Final value was 0, so nothing was removed, and value of delta t is 0.7. When you calculate all of them, so this root 2 and 0.7 is 1. Root 2 and into 0.7 is 1. If you calculate 1.41 into 7, this is nearly equal to 0.7. 0.7 is nearly equal to 1. So 10 to power minus 3 volt. So what we get? 10 to power minus 3 volt. This becomes 1 denominator, and above we have 10 to power minus 3 volt, which is equal to 1 millivolt. So this is 1 millivolt. Now we know what is the induced EMF. Induced EMF is 0.1, sorry, induced EMF is 1 millivolt. Now we have to calculate the current. Now remember the formula, V is equal to IR, I is equal to V upon R. I is equal to V upon R. So I is equal to epsilon upon R, because V is same as epsilon. So this is 10 to power minus 3 volt. Again remember, this is in millivolt and you have to put it here in volt. 10 to power minus 3 volt upon 0.5 ohm. So what you get? 2 milliampere. That means a very small amount of current is there, which is 2 milliampere. Note that Earth's magnetic field also produces a flux through the loop, because you know that Earth's magnetic field is also there, but it is steady, which does not change with the time, hence does not induce any EMF. So Earth's magnetic field is still there, but it will not produce any kind of induced EMF because it is not changing with time, especially in this very small time.